Welcome to this explainer. All right, let's dive right in. Today, we're talking about transients in power systems. Basically, the hidden complexities of our electrical grids. Most of the time, when we flip a switch, the power is just there. It's reliable, it's steady, but what actually happens behind the scenes to keep it that way? More specifically, how do these massive, sprawling networks survive sudden, catastrophic shifts in power that could otherwise just tear them apart? Well, that's exactly what we're going to unpack today. To really put this into perspective, imagine a calm, steadily flowing river. That's your grid on a normal day. Now, imagine that river instantly turning into a violent, raging flash flood, literally in the blink of an eye. This is the reality of an electrical tsunami hitting our high-voltage transmission lines when things go wrong. Like a massive lightning strike or a sudden equipment failure. The grid has to somehow absorb that unimaginable wave of energy without totally collapsing. So, here's our roadmap for today. 1. Understanding power system transients. 2. Triggers of grid disturbances. 3. The threat of overvoltages. 4. Defending the HVDC system. And finally, 5. Mastering reactive power. Let's get to it. Starting with Section 1, Understanding Power System Transients, the shock waves in the grid. So, what exactly is a transient? Well, by definition, transients are sudden jumps or brief, extreme changes in voltage and current within a power system, and they completely disrupt the normal operational flow. Instead of that steady, predictable flow of energy we want, transients act like that sudden tidal wave in a canal we talked about earlier. They threaten to overwhelm literally every single piece of sensitive equipment right in their path. When you compare the two states, the difference is night and day. On one hand, you have steady state operation. It's balanced, it's predictable, and the voltages are constant. It's peaceful, right? But on the other side lives the nightmare scenario, the transient state. We're talking chaotic jumps in voltage, totally unpredictable surges, and just severe, intense equipment stress. If the system can't survive this chaotic state, well, the whole grid goes dark. Moving on to Section 2, Triggers of Grid Disturbances. Where exactly do these tsunamis come from? The sheer scale of time we're dealing with here is honestly fascinating. Disturbances on the AC side basically fall into 3 categories. First up, steep front overvoltages. These are often caused by lightning strokes hitting the network, and they strike incredibly fast. We're talking 0.3 to 3 milliseconds. That is literally faster than you can blink. Then you have switching overvoltages, which happen when the system actively clears faults. These wavefronts last over 100 milliseconds. And finally, temporary overvoltages. These are often triggered by a sudden load rejection and can last a few seconds. So because each of these triggers has a completely different duration and intensity, each one requires its own unique, customized defense strategy. Now, the AC side isn't the only vulnerable part of the grid, right? On the direct current, or DC side, the system has its very own unique set of vulnerabilities. Here, steep wavefront surges aren't just from lightning. They're actually often caused by ground faults directly on a pole of the bipolar link itself, or they can come from sudden current jumps due to commutation failures inside the converter. Basically, that's when the hardware just fails to hand off the current properly. So what this means is that engineers have to account for a massive dual threat: internal mechanical failures from within and external strikes from nature. Which brings us to Section 3, the threat of overvoltages. Let's visualize the chaos. If you look at the wild, erratic spikes in these transient voltage waveforms, especially during the capacitive and inductive terminations, you can literally see the electrical chaos unfolding. Look at those sudden vertical jumps. That represents raw, destructive energy, actively trying to force its way through highly sensitive infrastructure. It's not just abstract numbers on a page. This is a literal physical assault on the grid. And there's a fascinating, honestly almost ironic point from the source material here. It notes that the dynamic overvoltages are mainly due to the excess of reactive power released by the sudden blocking of the converters. So what does that actually mean for us? Well, it means that when a fault happens and the system tries to protect itself by suddenly blocking its converters, it can actually inadvertently release a massive backup of reactive power. Crazy, right? In trying to stop one problem, the system's own defense mechanism can compound the issue and create a brand new dynamic overvoltage. Talk about friendly fire. Okay, Section 4, Defending the HVDC system, the shock absorbers for the grid. So how do we stop this? Well, right at the heart of an HVDC converter is the thyristor valve, and when an overvoltage occurs, a highly strict protective sequence takes over. The system instantly senses a dangerous forward overvoltage, which then triggers a tiny, hypersensitive component called a breakover diode, or BOD. This little guy initiates a protective firing of the thyristors. In mere microseconds, again insanely fast, the energy is safely shunted away, ensuring that the heavy-duty equipment survives completely intact. But hey, protective firing isn't the only shield we've got. Across these valves, engineers also place zinc oxide gapless DC surge arresters. You can think of these gapless surge arresters as the ultimate heavy-duty shock absorbers of the grid. Their entire job in life is just to sit there and physically take the brunt of external attacks, like lightning and massive switching surges. They absorb that transient energy so it doesn't destroy the delicate thyristor valves hiding right behind them. They essentially act as an invisible, self-healing wall. And that takes us to our final part, Section 5, Mastering Reactive Power, Regulating the Flow. Looking at the physical architecture here, you can see a schematic for a typical thyristor valve module on the left and a single-phase Thyristor-Controlled Reactor over on the right. I wanted to show this because these aren't just abstract theoretical concepts, right? These are incredibly complex networks of reactors, capacitors, and solid-state electronics that are physically out there, regulating these chaotic electrical forces in real time. Now, managing reactive power during a transient is absolutely required for three main reasons. First, to control those dynamic overvoltages caused by load rejection that we talked about a minute ago. Second, you need it for the speedy recovery of power following a fault in the inverter system. Because, if the power ramps up way too fast without voltage support, bam, you get a commutation failure. And third, to control overall system instability, especially in systems with low short circuit ratios. Mastering this reactive power isn't just some clever efficiency trick to save a few bucks. It is an absolute necessity for preventing total voltage collapse and keeping our lights on. To achieve this lightning-fast control, modern grids utilize static VAR systems, or SVS. These systems dynamically control reactive power demand. And the real magic of an SVS, it's the speed. Because they use fast-acting solid-state electronics rather than relying on clunky, slow mechanical switches, they can instantly shift the reactive power profile from capacitive to inductive. So when a crisis hits the grid, they step in and balance the system practically instantaneously. It is super impressive. All of this incredible engineering, from the surge arresters and the protective firing sequences to the static VAR systems, it leaves us with a pretty fascinating final thought to ponder. As our power grids grow infinitely more complex every day, integrating way more renewable sources and spanning vast geographical distances, we have to ask, are our digital defenses evolving fast enough to outsmart the next massive electrical storm? It truly makes you appreciate the invisible battle happening every single second just to keep our screens glowing and our modern world turning. Thanks for joining me on this explainer, and keep questioning the tech that powers our lives.